In this video, I'm going to teach you the fundamental concept needed to understand how an electric generator and electric motor work. They are different devices in design, but they share the same set of physical laws, and many of them can work in a reversible way, meaning they can convert energy in both directions. First, I'm going to show how a generator works and then how the same principle can be reversed to create a motor. Before starting, we need to understand the basics. An outlet with nothing plugged in has no current, but it does have voltage. Voltage is an electric potential difference that pushes electrons, and when those electrons find a conductive path, they move. And that movement of electrons is electric current. Conventionally, we say current flow from positive to negative, even though the electrons actually move in the opposite direction. With this, we can understand electromagnetic induction. This is called Faraday's law. When there is a change in magnetic flux, a voltage called EMF is induced. If there is a closed circuit, that EMF, including back EMF, produces current. The induced EMF is proportional to how fast the magnetic flux changes. That is the heart of any generator. To explain it better, I decided to design and build a homemade generator. The initial sketch showed a small DC permanent magnet motor, and on its shaft I added two pulley stages to increase the transmission ratio. For example, if one pulley has twice the diameter of the other, the smaller one will spin faster, while the larger one will have more torque, assuming an ideal power transmission system when power is conserved. For a generator to produce a significant voltage, it needs high angular speed. The easiest way to achieve that manually is by using pulley or gears, both of which increase speed. To build this generator, my first plan was to make everything from scratch, using a small plastic jar, creating the rotor, the moving part, with wirings to reduce friction losses. Inside that jar, I plan to add toppers made with screws to wind the conductor, which will be enabled coated copper wire. This is very important. The enamel is a dielectric insulator that allows multiple layers of coils without short circuit between adjacent turns. More turns increase the length magnetic flux and therefore the induced voltage, but they also increase the resistance of the coil, reducing the available current. After days of searching for a enamel-coated copper wire, I realized the price was outside my budget, so I disassembled an old angle grinder that still had a decent rotor. The direction of the winding is extremely important because it affects the polarity according to the right-hand rule. This determines the direction of the induced current and the correct interaction with other generator or motor components. After getting the rotor, I mounted it on a small wooden base with an whole metal clamp to hold it in place, trying to keep the center of the shaft as aligned as possible. For the magnetic field, I used weak magnets from Hall speakers, which reduce the induced voltage. In future version, I want to use neodymium magnet. The position of the magnet is also very important. They must be close enough so that most of the magnetic flux crosses the conductor. In a generator, besides increasing RPM, a stronger magnetic field produces a higher induced voltage. The first prototype was born, which showed how important thermal dissipation is. I started again with another rotor, better magnets, a better support, and instead of wires, I used brushes to transfer current more easily. We connected an LED to see that movement was producing energy. Of course, this is only a demonstration model, and to improve it, I will use better magnets, many more RPM, a better design, and more turns of wire. In this project, I received help from my classmates to get essential parts and to simplify assembly. If in a generator motion creates electricity, then in a motor the electricity creates motion. This is a much broader topic, with DC motors, AC motors, asynchronous motors, synchronous motors, three-phase, single-phase, and many more. But to keep the video short, I'm going to explain the DC motors. When an electric current flows through a conductor, it creates a magnetic field. The rotor's magnetic field interacts with the stator magnetic field, generating a force, the Lorentz force, that produces torque, making the rotor spin. To make the rotation smoother and more continuous, more coils are added to the rotor through a commutator. The commutator alternates the connections so the polarity stays synchronized with the rotation. This creates friction, so brushes are used on each side to reduce it. Unlike a DC motor, an AC motor naturally alternates the polarity of the current over time, creating alternating poles in the stator that push the rotor in the rotation. When I tested my prototype, I applied voltage to the commutator, but the coil had such low resistance that I supplied too much current and burned the rotor. Excessive current can generate enough heat to degrade the insulation. That showed me that the current was too high for that wire gauge, so I built another model with a better winding and it worked. Motors usually have many types of losses if they aren't well designed. Mechanical losses come from bearing friction, brush friction, and air resistance. Electrical losses come from the resistance of the conductors, yaw losses, and from eddy currents that hit the core. Magnetic losses include hysteresis losses, energy dissipated when the core's magnetization is repeatedly reversed, and losses from not uniform magnetic effects. There are also other small losses grouped as additional losses. So we can summarize it like this. In a generator, a voltage appears because of a change in magnetic flux. In a motor, a force appears that produces real torque when current interacts with a magnetic field. We could even use the energy generated by a generator to power a motor. Of course, my generator prototype can be much better, with a mechanism to reach higher RPM, stronger magnets, more turns of wire, or a better design. All the principles and laws I explained in this video appear and scale into many industrial machines that help us in our daily life in robotics, electromagnetics, renewable energy, and more. Thank you very much for watching this video until the end, and I invite you to subscribe so you don't miss future projects with explanation of interesting topics and to show how incredible and exciting this work can be.